So now we'll take a look at a couple numerical examples. In this first example right here, this is based on this circuit that's shown in the figure where I have two feeders. I'll assume that I have a monitor at the substation that's common to both feeders. Then I'll have two customer monitors at the bottom of each feeder. Then I'll be looking at the impact of two faults, one at fault location A and another at fault location B. Note in this case that for fault A, that this is going to involve a section between the substation and point 2 and a section between point 2 and A. It's the fault current's going to go through this line recloser here. And then the second case for fault B, the fault's on the main feeder. And so then you're going to have a fault impedance that's going to be dependent on the section of line between the substation bus and point B. But anyway, this is the scenario right here, and these are the monitoring locations that we have. So as far as the setup of this particular problem, it's a 12.47 kV circuit, and the substation has an equivalent impedance of 8% on a base of 10 MVA. You're given an X to R ratio in this case of 6, and so you're going to have to convert these into an R sub and X sub. And then for the line lengths between point 1 and point 2, this is 3 miles. This will be 336 conductor. Between point 2 and A fault location, this will be 0.5 miles. This will be assumed to be 1/0. And then between point 1 and where fault B is at, this will be 0.5 miles, and this will be 336. So the 336 is for the main feeder and the 1/0s for the lateral. Now, as far as the loading levels, you'll assume that we'll have 300 amps on feeder 1, 300 amps on feeder 2, and for the recloser on feeder 1 and 2, we'll assume we have 150 amps of load. And that's just so we can track the changes in net load that we're going to see at certain points on the circuit. So I'm giving you the assumptions to make for the positive sequence impedance for the 336 and 1/0. These are just some typical values based on some common constructions that we talked about before. So let's look at these two locations, location for fault A and for fault B. We'll assume in A that the recloser is going to be set up for fuse savings. We're assuming it's properly coordinated everything. It's going to operate on its fast curve within 6 cycles and reclose in 2 seconds. And we'll assume that we're successful in the first shot as far as clearing the fault. And I want to kind of estimate what we're going to see for the RMS current at the substation monitor and what the voltage is going to look like at both of these customer monitors. And then for fault location B, let's assume the relay operates within 3 cycles, it recloses in 6 cycles, and that this reclosing operation is successful in clearing the fault. So in both of these cases, we had temporary faults. And I want to do the same thing. I want to figure out what kind of current am I going to see at the substation monitor, and what am I going to see for voltage at the 2 customer monitors. So what we need to do if we're talking about the fault at A is we need to have an electrical model. And the electrical model is shown here where the substation has an impedance. This is fault A. The substation has an impedance. This line section between 1 and 2 has an impedance, and the section between point 2 and the fault has an impedance. And so the net impedance is the sum of these 3. This is basically the Thevenin impedance as seen from point A. So what I need to do is, first of all, I need to calculate the substation impedance. If I have 0.08 per unit, I multiply by Z base. So that's voltage squared divided by the power base. This gives me 1.24 ohms. And this is a magnitude of the impedance. So this is the square root of R squared plus X squared. So if I have an X to R ratio of 6, then I could say R is going to be X divided by 6, and I could use this for solving for X. So X sub is 1.23 divided by 6. This gives me the resistance. And then to calculate Z12, then I take the 336 conductor impedance per mile, I multiply by the length. It gives me a total impedance here. And for 1A, I take the impedance for the 1/0, multiply by the line length of 0.5, and this gives me the net impedance. So basically, to get IFA, I've got 12,470 divided by square root of 3 to give me a line to neutral value. Take the summation of these three impedances, and this gives me a fault current of 1913 amperes at a phase shift of minus 67 degrees. In order to calculate the voltage at the customer points, then what I'm going to need to do is, if I'm at customer monitor 2, I need this voltage drop for customer 2. But if I'm at customer monitor 1, then I need this voltage drop. I'm assuming that this load current is so low that I don't need to consider the voltage drop due to the load current. So basically, the voltage at this bus at the top of the circuit is the same as what the customer monitor sees. I know you have a hard time grasping that sometimes, but when we're talking about a severe sag, this 2 to 3% drop right here is going to be negligible compared to the amount of sag caused by the fault. So then if I want the voltage at customer 2, I take the source voltage, I subtract off the impedance that's common between the fault and that customer. And so multiply that by the current, I'm going to get 903 volts at an angle of minus 18 degrees. If we divide this by 7,200, this is going to be 12.5% of nominal. So this is a really severe sag. If I'm at customer 1 and I calculate the voltage at customer 1, well, the common impedance between the fault and customer 1 is just Z sub. And so in this case, then V source is minus Z sub times IFA. And this gives me a voltage of 4,910 at an angle of minus 6 degrees. And this is just the voltage sag down to 68.2%. Note that these terms in here are basically mutual terms that we were using before when we were using the Z-bus method in the earlier section on short circuit analysis. And so this is the Thevenin equivalent term, this is the diagonal term, and then these are off diagonal terms, which I'm just kind of getting from inspection from this particular diagram. So anyway, the next thing we want to do is just figure out, kind of visualize how this is going to change with time at the different points. So I said before that at the top of the circuit, I had 300 amps on feeder 1, 300 amps on feeder 2. And so if we draw this out, what I see at the top of the circuit before the fault events, I see the 600 amps. Then when the fault occurs, basically what I'm going to see is the combination of the fault current and the load current. Now, since the fault current is generally a lot greater than the load current, I typically just assume what that monitor sees as the fault current. If you want to make this a little bit more accurate, you can put the load current back in, but keep in mind that there's a severe phase shift on the current. Most of this current's reactive, most of the load current's resistive. And so the reactive current's dominating in this case for the magnitude. And then when the recloser operates to try to clear the fault, then basically when I'm losing, when this recloser operates right here, is I'm losing all this load, which, and I said I had 150 amperes worth of load there. And so what happens in this case is at the top of the feeder, at the top of the circuit, I should say, I see a change of 150 amps, so it drops down to 450. And when the recloser closes back in, it goes back up to 600. So from the top of the circuit, from the substation viewpoint, I see load current, I see fault current, I see a little bit less load current because some of the load's lost when I operate the recloser. And when the recloser closes and is successful, then I get this load current back. Now in real life, there'd be a little bit of a transit overage right here because whenever you interrupt load, you know, there's a load pickup current that's a little bit higher, but we'll ignore that in this case. Now at customer one normally sees nominal voltage. When the fault occurs, then we see the sag at the point of common coupling. And so this drops down to 68%. And when the fault's cleared by the recloser, the voltage goes up to normal. So what you can get from this is you get the depth of the sag, and then based on the protection, how long it takes that recloser to act, then that gives you the duration of the sag. Okay, so the faster the recloser acts, the smaller the duration. At point number 2, basically what happens is the voltage starts at nominal. During the fault, it drops down to 12%. But since the recloser has to open to clear the fault, the voltage drops to 0, and it takes 2 seconds to come back. And so basically that customer sees a 2-second outage. And if you have a complete outage, that 12% is kind of irrelevant, because if you have the outage, that's a lot worse than having a voltage sag. And so that's not a very good situation for customer 2, but it's maybe okay for customer 1. So if you go back to this case again, you know, the thing you'd have to be wondering is, if you were utility and utility operations are looking at this protection, do we want to do fuse savings here? The problem is, because of the fuse savings and that customer was out without power for 2 seconds, if we put a fast fuse in here, the fuse will blow really fast. It'll just cause a sag at this customer. It'll be a pretty deep sag, but that's probably better than having a 2-second outage. And this is where you have to look at the trade-offs. Now, on the other event, if we have the fault at location B, then the path's a little bit different. And so in the case, if we're talking about that other location, we're going to have fault current going through here. During the fault, since I have a 3-phase fault here, it's just going to drive that customer monitor voltage to 0. As well as we're going to have the breaker operate to boot. On the adjacent phase for customer 2, then basically what customer 2 is going to see is the voltage drop across that substation impedance. All right, so again, I'm neglecting this change in voltage that's just due to the load. I'm assuming that this is basically equal to 0. So in this case, if it's the fault at B location, then the fault current is the substation voltage divided by the net impedance to the fault. That's the substation impedance plus the impedance from 1 to point B. Impedance from 1 to point B is the line length times the 336 impedance per mile. And then when I substitute into here, I get this fault current of 4,547 amps at an angle minus 77 degrees. So highly reactive, mostly imaginary current. This drives the voltage down at that customer 1 to 0. And then on the adjacent circuit at customer C, it's going to be impacted according to the substation impedance. And so if I subtract off the voltage drop across that substation model, then this is going to give me 1,596 volts, which is a sag down to 22%. Anytime you have a situation where you have a fault up close to the top of the feeder, it's going to sag this whole substation bus down, and everybody on any feeder connected up to that substation is out of luck. And so this is a real worst case event, is to have these high fault current events occurring toward the top of the feeder. It's really where you'd want to do a lot of tree trimming to make sure you cut down the number of faults. So, excuse me. So anyway, when you look at the results of this, then, you know, basically you're going to see the 600 amps initially on the top of the circuit in the substation monitor. This is going to go up to 4,547 amps. And then basically what's going to happen in order to clear the fault, what we're going to be doing is we're going to be operating this circuit breaker up here. So we basically lose all the load on that circuit. So the current goes from 600 to 300 because you had 300 amperes on that breaker that just operated. So that current level drops down. And then when that circuit breaker closes back in again, then you see the recovery of the 300 amps. So this is what we would see at the top in the substation monitor. Voltage, customer 1, it just gets pulled down to 0. When the circuit breaker operates, it's going to be 0 still. And so you're going to have a net outage duration effectively of 0.15 seconds, the time that the fault was on, dragging the voltage down to 0, as well as having the voltage be 0 when you had the top of the feeder circuit breaker operate. On customer 2 location, it sees the voltage sag down to 22% for the time of the fault, which is 3 cycles. It's a pretty severe sag, so I don't know what's going to happen in this case for the loads. It's not a very long duration, so maybe those loads can ride through, but it's a pretty severe event because that fault was so close to the substation. Now, if you wanted to do some computer modeling for this, there's a couple ways you could approach it. One would be you do a transits analysis, and this is solving the differential equations. In the ECE 587 class we teach, we use a tool in there called PSCAD, which is a transit modeling tool. You could do the same thing in Simulink in the MATLAB environment with the power system modeling tools in Simscape. But what I'm doing in this case is I'm basically mapping these impedances into an impedance model in this case. And what I'm also doing too, just so I could show the loads, is I'm putting some current devices in here basically to look like constant current loads. And then what I'm doing is I'm putting these switches in here so I can model the response to the fault. Another thing I'm doing in this case, I'm putting in a ComTrade recorder so I could actually create a ComTrade file from this that I showed you in the previous example, in the previous section of the lecture. So anyway, what this particular program does, it does its calculations in the time domain. What it would do is it would actually compute the transits. It shows, you know, a little bit of a DC offset in the fault current. It could, you know, calculate the sag voltage and everything. This is probably overkill for a lot of distribution planners. This would only really be used if you had some weird issue you needed help resolving. So usually distribution planners don't run PSCAD, but if a utility had a power quality department, they might be using PSCAD for that, or they may actually be using PSCAD for their interconnection studies to look at like transformer inrush on PV farms. This shows a ComTrade playback where I've taken that result from the PSCAD simulation, actually playing that back on the Schweitzer relay view tool, where it can actually plot ComTrade waveforms. The one thing I wanted to mention before I move on to the WindMil case is that the nice thing about having ComTrade files as well is, let's suppose you wanted to play them back to a relay to see if the relay is going to operate correctly. What you can do is you can use these special power amplifiers to amplify, provide the voltages and the currents to the back of the relay. And so once I have the ComTrade file, you have like Megger is one company, Omicron's another company. You could take those ComTrade files that are digital, you can convert those voltages and currents, and then you could basically put into the relay the same types of waveforms that this relay would see in the field. And that's how we actually do testing a lot of times of the relay algorithms, is we take the computer simulations and we drive them back into the relay. So that's something else you can do with the ComTrade files as well. Now, one other thing I wanted to show you as well, let's go back to this scenario we talked about toward the beginning of the lecture, where we had the two adjacent feeders, and there's a customer concern on the non-faulted circuit. So you have a fault on here, and what we're going to see is we're going to see a sagging voltage at the top of the circuit at the substation bus, which is going to impact that industrial customer. To show you how this is done in WindMil, I'm kind of set up a simple circuit for this. Now, we've gone over how to do these calculations before, and this was covered in the short circuit analysis section. Nothing's really changed. You know, basically kind of what we're looking at is we're looking at a fault downstream, and we want to figure out, well, what's going to be the impact somewhere upstream. I just didn't do this in terms of two adjacent feeders. I had everything on the same feeder, but the principles are still the same. The sort of calculations you're going to be responsible for this section will just be for three-phase faults. Okay, we're not going to get into single-phase faults or line-to-line faults. We'll just kind of focus on three-phase faults. So the scenario would be that you have a substation impedance, some impedance up to the point of the fault. Maybe there's different fault locations you're looking at. And then you have some sort of power quality sensitive site on the adjacent feeder that you want to analyze. So you want to figure out, based on a fault here or here, what's going to be the voltage here. So what I did in this is I took this same circuit that I showed you guys for the DER part 3. This was a 23 kV circuit. And I looked at a couple locations for faults at the D2 node and also in the D6 node. This backbone is a 477 conductor. It's all the same. So the substation impedance, let's set that to 0.07 plus J 2.5. That's the source impedance. And what I'm interested in is I had an adjacent feeder, and I just kind of drew out a feeder. This is the second feeder circuit out of the substation. I'm interested, if I had a customer out here somewhere, what voltage it would see. So when you set this up in WindMil, what you need to have is you need to have a source impedance. And so if you have the source modeled in WindMil, even though it's regulating, what you do when you do the fault analysis is you need to put in some system impedance. Now, I didn't put a zero sequence impedance in here because I'm not doing imbalanced faults. If I were doing line to ground faults, I would need that zero sequence value. But since I'm doing just balanced faults, I'm just going to put in this positive sequence impedance in the source. What's going to happen when I do the fault flow, then it's just going to model this as a voltage behind impedance, okay? So even though you got the regulation checked, that's just for the voltage drop part. That's not going to be used for the fault flow. Then I'm going to have my feeder impedances, and these are exactly the same feeder impedances that we use when we're doing the voltage drop analysis. So, you know, this is 477 conductor, this is the construction, this is the length. And then to do this by hand and to compare this against WindMil, what I'm going to need is I'm going to need the positive sequence impedance. The way I'm going to get that is if I look in WindMil and I open up and I look at this set of overhead impedances, what I'm going to do is I'm going to take these values. I take the average of the diagonal terms to get ZS. I take the average of the off-diagonal terms to get ZM. So I'm assuming that this is actually balanced. In reality, this is not a balanced construction. They look at like phases A, B, and C in the neutral. This is a vertical construction, so the self-impedances are not actually the same. The off-diagonal values are not all the same, but I'm going to average each set. And then based on the average values, I'm going to calculate this positive sequence impedance, all right? So this is what I'm going to be using for my hand calculation. So anyway, if I have a fault at that first location, 1.7 miles from the substation, I take the voltage line to neutral, divide by the sum of the substation value plus the line impedance. 1.7 miles out, multiply by this positive sequence value gives me the line impedance. And then when I substitute in, this gives me a fault current of 3,683 amps. Then at the point of common coupling at the top of the feeder, then I simply take the substation voltage, I subtract off the drop across the substation, and this gives me 44,097 volts. And so again, if I go back to this diagram, what I'm doing is I'm assuming there's no load voltage drop on the circuit. What I have at the substation bus is going to be the same at any point on this adjacent feeder, right? So that's the assumption we're making. So anyway, just kind of keep note of this value 4,097. Now, if I look at fault location 2, which is further out, then I just simply have more line impedance. And so I redo this calculation with this new line impedance, and this gives me the fault current of 2,859. At the substation, I see 6,174 volts. And so this is only 47% of nominal. So the farther away I am from the substation, the smaller the fault current, the less stuff I have across the substation source model, I get less sag further away the fault is. Okay, so anyway, if I do this in WindMil, I can run a voltage drop study, and I basically see pre-fault what the values of voltage are. I see that basically what I have at this end of the feeder is 124 volts. It's basically the same on 120 volt base. It's basically the regulated voltage at the top of the feeder. What I do is I use WindMil fault flow, and what you do is you select where you want the fault placed, and so you select overhead line segment number 2. You pull up the analysis manager for fault flow. You'll see overhead 2 is selected, and you set this up for a line to ground fault, phasing A, B, and C. What this is going to assume, if I have 1 per unit here, that I'm doing these calculations assuming a source voltage of 1 per unit, which is reasonable, nominal. And then I get the fault results. And what the fault results show me is I'm getting 3 currents that are all different values. I'm getting voltages which are slightly different sort of values. So what's going on right here? Because before, what I had calculated is I calculated for the fault is 3683 for the current. Okay, so I had 3683 for the current, and then what I had for the voltage before was 4,097. Okay, so did I screw up on this, or what's going on? Well, what's going on in this case is that I did my calculations assuming that the line was balanced out as far as the distances between the phases. So that's what these numbers are based on. When WindMil did the calculations, it used the detailed model. And so it's making use of the fact that the off-diagonal impedances are not the same, the diagonal impedances are not the same, and you have such a huge amount of current that it makes a little bit of difference in your answers. So this isn't really too bad, but you basically see the 3683. I wouldn't say it's exactly the average of these 3 values, but it's kind of in between these 3 values. And the 4,097 is probably not exactly the average, but it's kind of in between these values. But it's the difference between assuming a 3-phase balance circuit and using a little bit more detail in the model, which WindMil uses. And so more than likely, if you were going to do this by hand, it's just to kind of get a handle on roughly what the drop's going to be. If you're going to do this more accurately, you're going to use a computer